Okay, so I plan on, just doing a quick review for the first exam. So this isn't going to be anything where I'm like delving deep into these problems. I just want to go over, what we talked about and what's going to be fair game on the exam, just so we're all on the same page. So the first place we started with was section 6.1. So this is the first one that's going to be on the exam. You need to know this stuff, from everything we've done before, obviously. But this is, we're testing on these concepts is the idea. So section 6.1 was area between curves. And we had two different integrals that we looked at for these. So there are two ways of doing this. So, if you have two curves that look like this, where you have a well-defined, top curve and a well-defined bottom curve, then the integral you want to use is the integral a to b, top minus bottom. And this one, the rectangles are going along the x-axis. So it's going to be dx. The other one we had was something that looked like this. So maybe something that looked like that. Here, top and bottom. Well, you could still maybe do that, but this one might be easier to do in terms of right and left. And then your rectangles are, going this way. Here your rectangles were, when I say rectangles, I mean, the Riemann sums that we're thinking about in terms of integration. So for this one, this area is going to be the integral from a to b. This time we're going to do right minus left. And this one, everything needs to have y in it. So if you're given an equation, y equals something in terms of x, you're going to have to solve that equation for x so that everything is in terms of y. I'm not going to, when I'm doing this, I'm not going to go into any examples because, the ones I would go to are the ones in the book, and I've already done all of those for you. So if you need, this is supposed to be like a really superficial, this is what we talked about kind of deal. So if you want to see more examples, go back and watch my lecture videos. We also talked about, what happens if I have something like this, and like, I can use two colors for that, can't I? And then something like this. So in this case, the top and bottom curve switch. So first, the black is the top, blue is the bottom, then it switches. So the way we dealt with this is we wrote a new integral. We said that the area is the integral from a to b, absolute value of f of x minus g of x dx. And in this case, f can be your top one, g can be your top one. It doesn't even matter because we have those absolute values around here. But the idea is, what you will end up doing is, so let's look at these intersection points here. So at these intersection points are where the graph changes. So let's call this A, B, C, and D. So if you're wanting to actually do this integral, you would break it up into, area is equal to the integral from A to B. And then, so let's call this top one F. Let's call the blue one G. So then, from A to B, it's going to be f of x minus g of x dx, assuming we're doing top minus bottom, not right minus left. And then we're going to add to that the integral from b to c. And now g of x is the top curve, the blue one. So g of x minus f of x dx. And then, if you want to go from c to d, you can do that. And again, f of x is back on top there. So it's going to be the top one. But the idea is, you're just trying to make all of these things positive. When we talk about area between curves, we want it to be a positive quantity because it's, that's how we want to interpret these areas as positive for this case. So that is pretty much section 6.1 can be summed up in those three integrals. So just be careful when you're doing these. If these functions have an intersection point at a spot that is not, the bound of your integral, so somewhere in between your integration bounds, the curves intersect, they probably change places at that point. So just make sure that you're drawing these while you're working out these problems. So the next one was section 6.2. We talked about volumes. And this one, the overarching idea was that, if A is the cross-sectional volume, so if A is a cross-sectional volume, then I can talk about of some, solid. And I think when I drew it before, I drew something that, looked like this. Kind of looks like a loaf of bread right now. But this is the idea. I have some sort of solid, and I can take, a cross section in here, and I get some sort of cross sectional area. The idea is, if I, find the volume, this tiny volume associated with this cross section, I can, add up all those tiny volumes, and I add up a bunch of, small quantities. That's called an integral. And so that gives me that volume is the integral of the cross section, d, whatever. So let me be a little more explicit. So we're typically going to be working in the x or y direction. So it's either the integral a of x dx or the integral a of y dy. And, the direction that you're integrating depends on, the direction that your solid gets extended into. So before I start with this area, then I extend it into a solid. Whatever direction I'm extending that solid into is my integration direction. Most of the time it happens to be, the direction that the the shapes are moving, but not always. So with the cylindrical shells, I have to be careful with those because it's not, the direction that the shells are moving, it's the direction that the shells are extending into. But we're not to shells yet. So, we talked about, there were two methods that we talked about first. So we had method 1, and that was disk method. I can't remember if it's C or K, and I can never remember what the disk or the difference is. So I'm going to guess K in this case. It's probably wrong. But so method 1 was disk method. And the idea behind that is, if I have, something, if I, take this thing and create a solid by revolving around, or like revolving around an axis. Let me use different colors. So if I have this shape and I revolve, around this axis down the middle, then I obtain a solid there. The idea is, if I cut into this in this direction, then these cross sections then are circles, and I can make a cylinder out of this. So the idea behind the disk method is I can write down the area of the cross section as it's going to be pi r squared. So it's just the area of a circle. And now the problem I have is to determine r in terms of x and y. So typically R is just going to be X or it's going to be Y. But, if you have, that's, if we, rotate about the X axis or Y axis, if you rotate about an axis that is off the, X axis or Y axis, it's going to be, it's going to be like X minus something or X plus something, depending on the situation. And all you can really do for that is you can draw it out and, label everything and then figure out, okay, is it 1 minus X? Is it X minus 1? And, I'm not going to write down some overarching formula because it might be complicated. I haven't put much thought into it. It's just, I think it's easier to just draw it. You need those skills anyway. You're going to need those skills anyway. Once you learn it, it's not too bad. So then once I have my area, I can write down my volume. It's going to be pi r squared. And then this is going to be maybe, so let's do this. So I'm going to do pi r of x squared or dx or integral pi r of y squared dy. So this r of y and r of x just means you write down a function for the radius in terms of x and y. Again, that's going to be that x minus 1 or y minus 1. Might just be x, might just be y. It just depends on your problem. You have to draw it out. The next method we talked about was washer method. And I think I saw something funny. This isn't talking about like, your washer sitting out in your laundry room. This is talking about, the mechanical part, the washer that you like put on a screw. So the idea behind this one is, I think the first example we saw was if you had a shape that looked something like this and you rotated it about the y-axis here, I could draw, you would get something that looks like this. And when you take cross sections here, you're going to get, this circle with a giant hole in the middle. It looks like a washer. So, when I draw this, I'm talking, this is, solid here. And then the inner circle is empty. And so we talked about it, you can imagine, the area of this thing, if this is, we'll call this, this blue one, R out. We'll call this green one, Rn. So area then would be, the whole area, pi r squared, pi r out squared. Here, let me do it like this. So it'll be the whole area, pi r out squared, and then I also subtract off the inner area. So I just take out that hole in the middle. And you can write this as pi r out squared minus rn squared. So whether or not you use, again, x or y depends on the situation. So typically, with these washers and discs, typically if you revolve around the x-axis, your variable is going to be y. Your variable will be x. For these washers and these discs here, So what that's going to look like is, if I have something that looks like this, and I rotate it around like this, I would use discs, and the direction these discs extend in will be the x direction. Whereas, if I rotate around the y, so if you revolve around, and this is typically, I'm sure there are counter examples for this, but if you revolve around y-axis, you typically take y as your variable. What this means is the radius will be a function of y, and this means the radius will be a function of x. And again, what that looks like is that first picture I drew. If I have something that looks like this, when I draw these discs, the thickness of the discs extends along the y-axis, and so that tells me that my integration variable is y. And then the last thing, the last thing we could do is, there was, what have I written? What word am I using? Method 3. The cross section was given. So this can be something like they tell you the cross sections are squares, So you can say the cross sections are triangles, things like that. So they tell you what the cross section is. And then your area will be, your area, your cross sectional area. You'll just write down, if it's a square, it's going to be the length squared. If it's a triangle, it's 1/2 the base times the height. And then you figure out those quantities in terms of the things you know. Okay. So I'm going to try and do, my goal is to do, so because these are extra videos, I'm not going to constrain myself to a certain time limit. I'm going to do chapter 6 as one video, chapter 7 as the second video. So end of chapter 6 was cylindrical shells. So the idea behind this one is we don't just have to constrain ourselves to discs and washers. We can also use shells that move as we revolve this. So the idea is, if I take this, cross section here, I can imagine rotating it around with this thing, and I'm going to get, this cylindrical shell. So it's a hollow cylinder with this small thickness here. And so I can do my volumes in terms of that. And so my area then will be the circumference of the cylinder, so the circumference of the circle that bounds the cylinder. So it's going to be circumference times height. And again, these are for you to figure out. You have to come up with an expression for the circumference. This is going to be 2 pi r. And then you also have to come up with an expression for the height. These are going to vary depending on what your axis of rotation is. So again, you have to draw it, you have to figure it out. That's part of the problem. I'm not going to write down an overarching formula because again, it's going to get complicated. You're going to have to think about it. I don't want to think about it. It's easier for me to just draw and figure it out case by case. Okay. So there are 2 ways of doing this then. So revolutions about, let's do the y-axis. So what I mean by that is you can revolve around the y-axis, but this also holds if you revolve around a line that is parallel to the y-axis. So that's going to be a line of the form x is equal to a. So you revolve around, like x equals 3, x equals -3, whatever. So I'm just trying to, give some insight into what your variables are going to be for this problem. So if you revolve around the y-axis, so this shape is the one I drew up there mostly. So what this looks like here is it's going to look like this. And so our integration variable for this case, last thing I should say is then that you're up here. So your area is the circumference times height. Volume then is the integral of the area, dx, or the integral of the area, dy. So again, if you revolve around the y-axis or the line x equals a, your integration variable will typically be the x will be x. So that tells you, your radius is going to be a function of x. And your height should also be a function of x. The reason being, when I take these cylindrical shells, the direction I extend them into, this little thing that I've just put in blue down there, that's the direction I'm extending it into. That happens to sit on the x-axis. So the direction that I'm going to extend into is the x-axis, or is the x direction. So my integration variable is the y direction, or the x is x. My integration variable is x. Similarly, if I revolve around the x-axis, so that might look something like this. So let's do this. So if I revolve this around the I revolve that around the x-axis, what I'm going to do is my cylindrical shells are now going to, their thickness is going to be in the y direction. So this one is a little weird, but it's, it's the same. So I'm going to draw these cylindrical shells that are going to go like this, and that's too low down there to be the same one. So they're going to look like this. So you can see now that the direction I've extended my cylindrical shell into is the y direction. So, if I revolve around the x-axis, or, a line parallel to the x-axis, the line y equals a, integration variable is going to be y, is typically. And again, this is because, I'm extending into the y direction. It's going to be an integral dy. So I need to have everything in terms of y there. So just one last note. All of these things, I'm integrating, something to do with the radius. So I'm integrating, in terms of a radius. So my bounds should only go So it shouldn't include the entire solid. That might sound weird. What I mean is, in this example up here, the only thing I'm going to integrate over is this, because when I'm integrating, I'm talking about a radius. I only care about half the whole thing when I'm talking about a radius. If I were doing this in terms of diameter, maybe I would integrate over the whole thing. But I only want to integrate over one part of this solid. All of the other half is taken care of. By all the math I've done beforehand. So this, when I talk about an integral from a to b with these things, that integral just extends over half of the solid that I've drawn. So that is chapter 6. It's a quick, again, this is a very superficial review. I'm going over some important points, going over some formulas that are important. So I'm going to stop here. I'll post this video, and I'm going to also do one for chapter 7.